Semvision is a Swedish technology company developing the market's most resource-efficient cements. Circular, ultra-low carbon cement binders made out of industrial byproducts. Visit www.semvision.tech to learn more.
Great. Okay, now we go to much more science, and I'm not too far on the science side. I will try. I'm Barbara Lothenbach, and I want, as I'm the first time in this audience here, I want to give you a little bit of a backup for myself. I come from Switzerland, not from Sweden, and I did grow up near the Lake of Lucerne, where you have now a nice picture, but actually I did grow up somewhere below this gray thing. I studied at the environmental science at University of Zurich, TTH of Zurich, sorry. I was also in Tasmania, where this nice picture comes from. I worked for an engineering company for 6 years, doing all kinds of different work. Then I went back to Oh, yeah, I should read my own slides. Anyway, I worked for an engineering company. Then I went back to science. I started at Empa, that's the Swiss Material Research Institute near Zurich, where I do cements and thermodynamic modeling. And since 2017, I also spend a part of my time at NTNU in Trondheim. And the picture you see there was taken this summer. Okay, the weather was like here now, but and the other thing is from Empa, and that's our unit for innovative materials. So that was a short introduction about me. Now I would love to go too much more into science. I want to speak about Portland cement, about the effect of limestone, about blended cements and how we can use thermodynamic modeling to understand it. And I will end with magnesium oxide binders, because I think that's one of the possibilities we have to significantly reduce CO2 emissions. I want to start at the beginning and give you just a few slides trying to explain what is thermodynamic modeling. Basically, on the left-hand side, you see the ingredients of a traditional Portland cement clinker. You have the clinkers, you have a number of minor minerals like gypsum, anhydrite, calcium sulfate, kalium sulfate, and so on. You have water. And basically what we do with thermodynamic modeling, we try to predict which phases we form. And we do not just predict, but we use thermodynamic data to figure out which is the most stable phase, and so we don't have to guess, and we don't have to define rules in beforehand, but the model will predict it based on solubility data and things like that. And as we already seen today, there will be on the 6th of December, there will be a webinar about thermodynamic modeling, and Claudia de Wert from NTNU will explain it in much more detail. So you have a second chance to get it. So how does it work in more details? This is, you see, this is a beaker of water, and we add some gypsum or anhydrite to it. And then basically the program can calculate based on different complex formation constants and solubility constants, which phases will form, how much will dissolve, whether we only have calcium and sulfate or do we have additional complexes. And the cool thing about that is generic data. So anybody can measure it in the lab, you can put it into the software, and then it's valid in the lab for your concrete, or even in nature when you have a gypsum deposit. It's all the same data, and so it's real prediction. And all the rest you don't have to care, the software will take care about that. Even though the equation look very cool. And maybe a last slide about that, it's also to what we know, or what we knew since many years, is the general database, the solubility of gypsum of Portlandite. That is well known. Our work was to complete that with data specific for our cement mineral. So CSH, Ettringite, AFM phases, and all that. And we have put that all together. We call it SEM data. We update it regularly to include more and more new and different cements. And in case anybody wants to use it, you can download the software and the tutorials freely. There's videos who can explain you how to do that. But I will not do that here. So now I want to get a bit more realistic. What we modeled here is the effect of limestone on hydrated Portland cement. So we just assumed everything has hydrated, and then we replaced 0 to 10% of the Portland cement by limestone, and calculated how would that change the composition. And the main part of the cement is CSH, Portlandite, but we see a difference in the phases further above, where there is monosulfate, ettringite, and monocarbonate. And basically what happens, if we add calcite or limestone into our mix, a little bit of the limestone reacts. And the cool thing it does, it stabilizes monocarbonate and leaves all the sulfur there to make ettringite. So it's the combination, and as ettringite, as you all know, ettringite is a very, very good space-filling material. We also can calculate an increase in the volume. You can see here this, if you look on the total sum, we have a small increase in volume, and I will show you in the next slide that this can be translated also in higher compressive strength. But first let's check whether this makes sense. I put on the left-hand side in green an XRD of the samples which would be on the left-hand side, and we see ettringite and monosulfate. If we look on a sample which contains 4% of limestone, then in fact we see monocarbonate instead of monosulfate and more ettringite, so in fact confirming what we predicted. Else I wouldn't show it, to be honest. But maybe much more important for you, if you mix together, if you have an old cement which does not yet contain any limestone and add a bit of limestone to it, you in fact can see a series of a maximum at around 2 or 3% limestone and then going down. And the other cool thing is also maybe up to 10 or 15% replacement, you will have the same compressive strength as a old Portland cement, which did not contain any limestone. And I must say, industry has figured that out before we understood what happened, because this was introduced maybe 20 years ago. But the understanding also helped us to figure out what was going on. And it's also the fundament for the development of the more blended systems like Portland limestone, calcined clay cement. Because when you understand what you're doing, that you make more and more ettringite, you can play with it. So another way to use thermodynamic modeling is to look on cement hydration. This is just an XRD of a hydrating cement, where you see that the clinker react and we form Portlandite, ettringite, and CSH. We also can quantify it, and then we get graphs like that. Or we can look at it with the microscope, and then we see these beautiful pictures where we have the reacting clinkers, we have the hydrates that grow on top of it, and after a few hours they start to connect and we get our concrete strength. You all know that. We also can do a completely other tests, and that is pressing out pore solution. What we do then, we basically hydrate a cement completely normally. We keep it in plastic bottles because we don't want to lose any humidity. And then we put them into into a big steel die, which you see here, and put that under our biggest press we have in the lab. And it's a bit like pressing water out of stone. It works. You can collect some solution, maybe 10 milliliter per kilo, but you get something out, and you can analyze that. And if you analyze that, you normally get a picture like that, a lot of hydroxide at high pH, a high sodium and potassium concentration, initially also high calcium and sulfate concentration, which goes out as soon as you deplete your calcium sulfate carrier. Why is it important? We think it's important because all the reaction in the cements, they go via the water. Because the clinker, they dissolve and then you form new solids. So you can use the composition of the water also to understand which reactions are happening and why do they happen faster or slower. And I can tell you all Portland cements, they look very similar to that picture. There's small difference. Then we said we also want to model, and we want to understand what makes the strength development in our cement. And maybe because we all know when the cement hydrates, we get more and more strength, and this has to be related to the formation of more and more solid. And we also know the higher the solid volume is, or the lower the porosity, obviously, the higher our compressive strength gets. Then we said, okay, we have a restrained dissolution of our clinker. The clinkers, they do not react fast, they react over days, weeks, months. And so we looked in literature and found a very simple equation from a paper from 1984, which just needs the surface composition, the surface area, the water-cement ratio, and the amount of clinkers, and gives you a reasonable hydration speed, which agrees well with what you see by XRD. Then we put that into our software, and if we restrain the clinker reaction, we can then start also to predict the hydration of a Portland cement, as you see here. So if the Portland cement hydrates, you have less and less water, which is plotted here in blue. You also have something which we call chemical shrinkage. And chemical shrinkage is just due to the effect that bound water has a lower volume than free water. And that's what you can measure if you do chemical shrinkage measurement. And the third thing you can see, the solid volume is increasing, which is the reason why we start to have more and more strength in our system. And this picture you've seen before, it's basically the picture of that hydrating cement, where we first make ettringite, and after a day or two we start to make monocarbonate or the AFM phases. One can do the same kind of modeling, obviously not only for Portland cement, but also for any kind of blended cement. There, normally the big problem is to figure out how much of your metakaolin or fly ash or slag really reacts. And this is the thing we cannot predict. We have, you can look on literature and find some general rules, but it's not so easy to figure that out. And that's also why we need all this, for instance, the R3 test, where you can see a bit the reactivity of your cement. And naturally, you can also relate the volume, or rather the porosity or the pore space, to mechanical properties. As I show here from a paper I have written with Magic Science from Heidelberg, to make that link as well. And you have a good relation between the gel spatio we calculated from modeling and the compressive strengths we have measured. But this only works for compressive strengths. We will not predict a lot else. And naturally, we also can model the pore solution. We can model how high the pH will be, how high chloride concentration could be, and things like that. Okay, but this was mostly on Portland cement. But you want to, I just wanted to summarize a bit the effect of limestone. I didn't show all the things I would have about it because we don't have so much time, and I want to speak about blended systems and other systems. But if we add limestone to Portland cement, we have a faster clinker reaction. We stabilize the ettringite. We have more volume. We have more strength. It's cheap. I haven't even written there. We can boost the effect by adding other SCMs like metakaolin, like fly ash, and similar things. The effect itself depends a bit on the sulfate to aluminium ratio, because this is the thing that determines how much ettringite you will form. Now, what I already thought I would say before is I want to speak a bit about COT, about alternative binders. And you all know there's a number of different strategies to mitigate CO2. We have heard a lot about that. And naturally, to mix anything with the cement to lower the CO2 content or the Portland cement in the mix is an obvious solution. And we also have now started to have a lot of that into our standards. And we've seen these slides already at least 3 or 4 times today. And yes, there's a limited amount of some things, especially slag and fly ash will also go out due to other reasons, because they hopefully will stop to burn too much coal. And the slag process is changing. So we have also to think on new ways to go there. And I'm sure we also have seen that today. We already use a lot of SCMs, or to some extent in our cements. I want to take a step back and put them on the ternary diagram, where we have down here the limestone and then the Portland cement, and then in different colors a lot of fly ash and slag and metakaolin and zeolites or whatever you want to add. Basically what you do always, you move from the calcium oxide edge up to the silica and aluminium edge. And naturally we also can use thermodynamic modeling to figure out what's happening. This is an example from Portland cement mixed with fly ash, and the Portland cement itself contains some limestone. So basically what you do if you mix fly ash in the system, you start to consume the Portlandite, because the fly ash is rich in silicon and aluminium, and you start to make more and more AFM phases, monocarbonate, and eventually straightlingite. The third thing you do is also you lower the calcium to silica ratio of your CSH. And this is just an illustration on how you can use thermodynamic modeling to understand quantitatively what should happen in your cement. Naturally, it's more complex in reality because the cement is also heterogeneous, and sometimes you see phases which should not exist at the same time. They do exist. And before we have spoken about the effect of limestone on Portland cement, but there was a work of Cloutier de Wert who also showed if we combine limestone, Portland cement and fly ash, then we get a more effect. Because again, we can make, as we have more aluminium in the fly ash, we have a higher potential to make more ettringite in our system and to have this beneficial effect. And in fact, you get a nice strength gain. Maybe if we just compare here the strength gains of a Portland cement and the Portland cement fly ash limestone blend, you can see you can get quite nice strengths if you mix them properly. And this was a replacement, 35% replacement. And maybe just one last word in that. The same trick is also for the so-called LC3 or calcined limestone Portland cement. You just use, instead of fly ash, you use calcined clay to give you more aluminium, and then you balance it nicely with the limestone to optimize the amount of heteringite you might form. And as I was supposed to speak about thermodynamic modeling, you also can use modeling to make so-called ternary diagrams. I plotted here the total volume. And if I plot here the composition of a typical LC3, you can see it's exactly where we still have quite good volume, although we can replace 50% of the Portland cement by limestone and metakaolin. But you also could do similar ternary diagrams for fly ash or for the VPI from Iceland or whatever you can think of. And I think this kind of instrument just helps us a bit to figure out what makes sense and where do we best look afterwards to do the experiments. And I haven't said it clearly yet. I think thermodynamic modeling is great, but it's basically worthless if you don't do experiments to go with it. Because there's the reactivity which we have no handle on. We can understand sometimes afterwards, but we cannot predict it. And naturally, one also can do the same ternary diagrams for different phases, but I don't want to spend too much time on that. I wanted to show some strength data. This is from a LC3 cement, where you can see up to maybe 50% of replacement. You get very nice compressive strength. You can get a similar picture also for fly ash cement, although there you have to get a bit lower replacement, maybe 35. And I'm sure you also can get similar pictures for the VPI cement or whatever you choose to mix. If we listen to some talks, I have often the impression LC3 is supposed to solve everything. It solves a lot. We can replace 50% of the Portland cement. But if we look on the energy, embedded energy, or the CO2 per kilo cement, we also can see it's good, but maybe there are other options which would give us even better possibilities, like a fly ash or a VPI or whatever cool SCMs you can think of. It's I think sometimes we have to take a little bit of a step back and think, yes, it's not only the cement replacement, it's also all the rest we have to think of. And maybe as I speak about CO2, or as today we have spoken a lot about CO2, I did bring an animation of one of my colleagues, and this is basically, the left-hand side is our CO2 emission, and it's a game, it's a play in the mind. What happens if we would emit zero tomorrow? And basically now we see the atmospheric CO2. It's in German, sorry, but I'm sure it's not too far. You see it goes down, but not very fast and not where it was, because CO2 loves to stay in the atmosphere. And we also can have a look on the temperature, and then we start to be slightly depressed. Now, the question is, how long do you think my scale is? 10 years, 100 years, 1,000 years? 100. It's unfortunately 1,000 years. So it's slightly depressing, but one also can look it differently and saying net zero, what we want to have in 2050, just should be the beginning, and we have to do something actively to lower the CO2 in the atmosphere, because it will not go away easily by itself. It just loves to stay there. And so I come to my last topic, and that's the magnesium oxide cements, or basically how can we change how can we get away from the calcium oxide or the calcium carbonate, which makes us so much troubles. And I put on the left-hand side a typical Portland cement composition. On the right-hand side, the elements we find in the earth crust, and naturally the solution has to be something we find in the earth crust. So we cannot use zirconium oxide or something because, yeah, you all know, we produce so much concrete, it makes no sense. And so basically, this is a very, very flashy slide. I wanted to say, at the moment, if we build Burj Khalifa, we will, just from the cement, we will make 200,000 tons of CO2 emission. And the hope is, if we would use magnesium oxide cements, we could bind 200,000 tons of CO2. However, that might be a bit too ambitious. What do we want to do in such magnesium, or what do we want to reach for magnesium-based cements? We want to develop something that's similar to a Portland cement, that you can handle similar easily. It should have similar strengths, and naturally it should have at least as good long-term durability. At the moment, and I will explain you a little bit more in a few minutes, we also have a lot of challenge. We have a poor workability. We have the risk of a late transformation of one phase to another. The reaction can be too slow or too fast. So this is one of the topics where we need to do a lot of research. And actually, this is a slide just from a new research project we started this year. So what is the idea? The idea is to use magnesium silicates. And magnesium silicates you have in olivine or phosphorite. And it's already used nowadays for carbon capture and storage solution. Basically, they dig it out, they grind it, they put it on beaches or agriculture and land. And then you have to wait a decade or two. And then thermodynamics, to come back to the topic, dictates that you form magnesium carbonate and silica. So you can get some CO2 out of the atmosphere. But you also can do a carbon capture and use approach. You can make a cement out of the magnesium oxide you have in the magnesium silicates. So you have a sort of a double effect. You have the CO2 binding by the magnesium oxide, and you can replace the Portland cement production by something else. So the first question is, where do we get the magnesium oxide from? The traditional thing would be to use magnesite. That's completely stupid to do, because then we just make the problem worse. Magnesite is also, you need to heat it to get magnesium oxide. It's not available everywhere. There's other uses for magnesite, so it's really not a good idea to use that. However, we have magnesium silicates, and this is a map from a paper of Scott et al. In 2021, where they figured out where on Earth we have magnesium silicate near the surface. And yes, I can see Sweden is not very on that map. Norway is, Switzerland is, so we are different. No, it's available on a lot of places, and I'm sure it's also not complete, this list. The second question is, do we have enough? And he also looked on that in his paper. He figured out how much we would need to compensate all anthropogenic CO2 in a year, and to take away an additional 26 billion tons of CO2. And if he do that, he ends up with the red box, and basically the deposit in Onan would last for more than 1,000 years. So if we go a bit down and think on a cement scale, you can produce all the cements you want just from these single deposits, and there are many more. So that's not really the problem. The second problem is maybe how to get it out. That's a bit more challenging. There's at the moment a number of different groups in New Zealand, in Finland, and I think also in Norway, working on the topic on how to find a technological solution to divide the magnesium and the silica into two parts. Another source of magnesium is also the brines from drinking water production not here. I'm sure you have enough drinking water, but there are many areas in the world where they have to produce drinking water from the seawater, and seawater is really rich in magnesium. And this would be one of these good options to use this brine. So, now we go back to the cement after I tried to explain you that we can find the magnesium. Magnesium carbonate cements are basically based on mixing magnesium with a source of carbonate and water. And the source of carbonate can be already a magnesium carbonate, for instance, hydroxymagnesite or nesquionite or whatever, or it can be bicarbonate or carbonate solution. If you do that, you start to make something which we called, until very recently, hydrated magnesium carbonate phase. Basically, we didn't know what it was, but at the same time, you also get a compressive strength here on mortars of around 30 megapascal after 1 day. And for comparison, we have also put a traditional Portland cement and the same 3A. And actually, even the concrete or the mortars looks exactly how normal mortar looks like. You also can do fresh concrete testing with it. You can do slump test. Actually, I didn't note it here, but you have to add a lot of PCEs to get a good slump, but you can solve it, and then you can make all kinds of testing cubes and prism. And obviously, you also can measure concrete strength. This is now an example of a 70% magnesium oxide and 30% hydromagnesite mix. And there we have compressive strength after 1 day of 25 to 30 megapascals. And it increases to 35 or 50 megapascals using a traditional PCE. This is one of the big problems we have is to get really to work on the workability, to get optimized PCs, because the ones that are on the market are made for Portland cement, obviously. We also looked on drying shrinkage. It has a relatively high volume stability, at least the mix we looked at. It has, in addition, a moderate expansion at high relative humidity. We don't know exactly why, but we just observed it. And then we also thought we want to understand what's going on a chemical side. And this is an isothermal colorimetry picture. In black, you see the magnesium oxide, which goes to bauxite, and it doesn't happen. It doesn't generate a lot of heat. In blue and red, you see the mixes with hydromagnesite, and if you add hydromagnesite, you get much more heat, and you also get much more strength. I did not put here the black points, which would be the magnesium oxide or the bauxite, because basically they just don't produce any strength. So we cannot make bauxite cement. Then the question is, what is the binding phase? It cannot be bauxite, because we know bauxite doesn't work. So my colleagues made a lot of experiments in the lab. They made pastes, and then they studied it with all the methods we could find in our lab. And one of them is obviously the XRD. And if we look down here, we see, I know I will be finished in 5 minutes. We see the bauxite, and if we have the hydromagnesite mix, we still see a peak at the similar position as the bauxite, but it's much more broad. So it must be something less ordered. We didn't find any new phases. We've seen half of our initially added hydromagnesite was consumed. The broad reflection I already mentioned. We could see some additional reflections, but we didn't see any really new phase. So we didn't really know what we thought. We also did analyzed the gases if we heated the samples on TGA, and one thing we can see, we start to have some gale water in the mix, and we release the carbonates at the same moment as we release the water from the bull site. So we also tried to figure out where is the carbon, and we did some solid state CNMR, and there we've basically found two unknown peaks, which just told us we have somewhere a carbon in our structure. And to make it the long story short, we then went one step back and thought maybe it's a disordered pool site, and we used XRD to mirror what would happen if we would allow the pool site, which has layers like that, to move in this direction and this direction and this direction. And if we do that, then we in fact could reproduce what we've seen before experimentally by the XRD. So what we think at the moment is that we sort of, the binding phase in such magnesium carbonate cements is a disordered pool site which has water and CO2 in its structure. And naturally, we also did thermodynamic data for this system, and we modeled our system. And if we do that, we can nicely match the experimental data. So we think, we have halfway an idea on how these phases looks like. Here is a picture of a PhD that's going on, and here we just added different amounts of carbonate in the system, and you see the more carbonate we add, the more we can see this hydrated carbonated pool site, and the more we also can take up. And this is my second last slide. I did speak a lot about magnesium oxide and adding carbonate to it, but naturally you also can add again the silicate or metakaolin or fly ash or slag to it. And I will not speak about that, but you can get very nice and interesting mechanical properties if you do that. And that's what we are investigating in our project. So maybe to summarize also the magnesium oxide part, we can make magnesium carbonate cement. They have a relatively high early strength. They are potentially CO2 negative. We still have a lot of open questions. We can look on mixed magnesium carbonate cements with silica and metakaolin, and they seem to be very promising. But there's also many open questions. We don't know yet exactly where the magnesium oxide will come from. We have poor workability. Often the reaction is rather slow. We are not sure what happens in the long term. We have the risk that we might form something else than the HCB. We've seen relative humidity as a strong effect. And basically, in other words, we need a lot more experience, or we have to go and put these things out in the environment and see what happens before you really want to sell it. We also have a low pH. We did some preliminary experiments. It didn't lead to corrosion. We thought it's probably because it's very dense, the material, but that's also a thing we have to think about. And also, to be honest, it works in the lab, but it's nothing you will be able to buy or produce yourself in the next few months. It really needs much more thinking. So I want to close with this slide. CO2, net CO2 is just the beginning. Thank you for your attention.
Thank you very much.
Thank you.
Yes. You have a question?
I have none. You have a question?
What is the specific area for the magnesium-based cement?
Anything. You watch the concrete watch. I think at the moment, we have this unit I showed the picture in the beginning, and we really want to make an outside wall there, and the bench sitting outside. And if I would have to use it today, I would use it for interior, where we have a bit more control about the environment, and not in the shower, to be honest. But it's I mainly see the potential and a lot of open questions.
It looks like you're having some development to do, but you believe in, of course you do. Otherwise
I do believe in it. I think it's very cool. It seems to work well, and the results.
And we all need people like you to try to do things.
Yeah.
Don't you agree?
Vi vill att betongkonstruktioner ska hålla länge. Det spar kostnader, men framför allt spar det naturresurser. Därför driver vi utvecklingen av produkter som förbättrar betongens bärförmåga, beständighet, förstärkning och skydd. Tillsammans bygger vi en hållbar framtid.